Hello everyone, and welcome to video number 3. In this video I shall be covering the method of determining the enthalpy change of reactions when given enthalpy change of formation values, and thus the title Enthalpy Change of Formation Energy Cycle. We will be constructing energy cycles as in the previous video, but this time using enthalpy change of formation values instead of enthalpy change of combustion values. A quick reminder, the enthalpy change of formation definition is the enthalpy change when 1 mole of a substance is formed from its elements in their standard states under standard conditions. I'm going to use the same example I used in my previous video, which is 1 mole of A reacting with 2 moles of reactant B to produce 1 mole of reactant C and 3 moles of reactant D. And we are required to calculate the enthalpy change of reaction for this reaction, given the experimentally determined enthalpy change of formation values for each of the reactants and products. Thus here, if given the enthalpy change of formation values for both reactants and products, calculate the enthalpy change of a particular reaction. This is the type of cycle we would construct. The definition of enthalpy change of formation is when 1 mole of a substance, as here, as A, is formed from its elements. Thus, the arrows in this example would be pointing upwards from the intermediate towards the reactants and products. Unlike the previous in the previous video, when using enthalpy change of combustion values, the arrows would be pointing downwards according to the definition, which is when 1 mole of a substance is combusted to form CO2 and H2O. Thus, these arrows here represent the definition of enthalpy change of formation. Thus, in this example as seen here, I have 1 mole of A. And to form 1 mole of A from the elements, this represents the enthalpy change of formation of A given in kilojoule per mole. Since I have 1 mole here, this has been multiplied by 1. The same applies for reactant B. By definition, it's the enthalpy change. The enthalpy change of formation is the enthalpy change when 1 mole of B is formed from its elements. But here we're forming 2 moles of B, and thus the enthalpy change of formation would be multiplied by 2. The same applies for product C and product D, which is multiplied by 3 moles here. All arrows, when given enthalpy changes of formation, are pointing upwards, while when given enthalpy changes of combustion would be pointing downwards towards CO2 and H2O. Here I would list the elements that would make up the atoms in both reactants and products, and I would balance these elements to produce the same number of atoms in either the products or the reactants, as I will display or in the next example. Thus, to calculate the enthalpy change of this reaction here, one would have to go from this end of the arrow to this end of the arrow through a different route, which we have constructed here. Thus, we need to go from reactants to products via a different route than this arrow here. This would be going from reactants to products in this direction. Thus, in this case, when using enthalpy changes of formation value, I'm going to have to change A into the elements, B into the elements, and then from the elements form C and D according to the stoichiometric ratios listed. Therefore, I would have to move against these 2 arrows, and thus I would flip the sign of the reactants in this case. Unlike in the previous video, we flipped the sign of the products in that case. In this case, we will keep the sign of the products as is, because this represents the enthalpy change when 1 mole of C is formed from its elements. And this arrow represents when 1 mole of D is formed from its elements, and since I have 3 moles here, I multiplied this by the value of 3. This would be much clearer if we were to solve an example, which I have listed below here. I have also listed in general, I've shown that the enthalpy change of this reaction would be the enthalpy change of the product C plus the enthalpy change of formation of product D multiplied by 3, subtracted from the enthalpy change of formation of A minus the enthalpy change of formation of B multiplied by 2. Therefore, when using enthalpy changes of formation values, the second method could be generalized without constructing an enthalpy or an energy cycle, could be generalized as we will always to calculate the enthalpy change of reaction when given enthalpy change of formation values, the enthalpy change, the sum of the enthalpy change of formation of products minus the sum of the enthalpy change of formation of reactants would produce the enthalpy change of reaction listed here. As you can see here, this negative sign has been added to flip the signs of the reactants, since we will be moving against this arrow in the opposite direction. Thus, if this were an endothermic reaction, I would flip its sign and convert it into an exothermic reaction, because I would be moving in the opposite direction. Let's solve an example to clarify this further. Consider the following enthalpy changes given in kilojoules per mole. I'm going to raise the screen here. Thus, I'm given the enthalpy change of formation of Fe2O3 here as negative 822 kilojoules per mole, which is a reactant here. I'm given the enthalpy change of formation value of CO gas per mole in kilojoule per mole, which is negative 111, and CO is a reactant here. I'm given the enthalpy change of formation of CO2 gas per mole, which is negative 394 kilojoules, which is a product here. I'm not given the enthalpy change of formation of iron solid here. This is due to iron solid being in its standard state, and as stated in the previous videos, the enthalpy change in video number 1, the enthalpy change of formation of an element is equal to 0. Thus, this element has no enthalpy change of formation to form it from its elements. Thus, it would be 0. The first step you would take to construct an energy cycle using enthalpy change of formation values is to place the elements that make up either the reactants or products down here, which would represent the intermediate. I'm going to use the products. They are the same moles of atoms in the products and reactants, so you use either the reactants or products. I'm going to choose the products here. So I have iron, and iron's elemental form is Fe solid, because I need to add the elements that make up the products here. And I have 2 moles, and thus this is 2 moles. Plus, the other elements that make up the products are carbon solid, and I have 3 moles of carbon, so I would multiply this by 3. And oxygen exists as O2 gas in its standard state, and I have 3 moles of oxygen gas, thus I would put 3 moles here. Thus, this intermediate here represents the elements that make up either the reactants and products. The balancing of these elements has nothing to do with the multiplication of the enthalpy change of formation values, and thus would never affect your answer. It's just to have the cycle, all the atoms in the cycle balanced. Thus, I'm given the enthalpy change of formation when 1 mole of Fe2O3 is formed from its elements here. Thus, this is the arrow I would draw, which represents this definition. It's the enthalpy change when 1 mole of Fe2O3 is formed from its elements. Therefore, this arrow would represent negative 822 kilojoules per mole in this direction. On the other hand, I'm also given the enthalpy change of formation of CO from its elements per mole, but I have 3 moles here, and per mole it's negative 111. Therefore, I would multiply this value by 3. So it's negative 111 multiplied by 3. This represents this arrow here. I do not have an arrow to form Fe solid from 2Fe solid. This would be 0 value, thus no arrow will be drawn. I also have the formation of CO2 per mole from its elements, which is negative 394 kilojoules per mole, but since I have 3 moles here, I will multiply this value, negative 394, by 3. Therefore, the enthalpy change of this reaction can be calculated by moving from reactants here to the products here through the cycle, to go from this side of the arrow to this side of the arrow through the new proposed pathway. Thus, I would have to move against this arrow and against this arrow, and thus their signs need to be flipped. But I will be moving along this arrow, and thus this sign would remain the same. And I would add all these enthalpy changes of reaction. Therefore, the delta H of reaction would equal 3 multiplied by negative 394, since the sign of this enthalpy change will remain the same, and I will subtract negative 822, which would become a positive 822, and I would subtract 3 multiplied by -1, 11, which would also become added or become a positive value. Thus 3 plus 3 negative, sorry, this has already been multiplied, thus this would be 1, 1, 1. This follows the general rule for when given enthalpy changes to calculate enthalpy changes of reaction when given enthalpy changes of formation would be which equals the sum of the enthalpy changes of formation of the product minus the sum of the enthalpy changes of formation of reactants. And this is what was done here. The sign of the products remained the same, while the signs of the reactants were flipped, which is the function of this negative sign here. Thus, a quick recap regarding the energy cycles we learned so far. When constructing an energy cycle for a reaction using enthalpy of formation values, the arrows will always be pointing upwards towards the reactants and products, from the elements towards the reactants and products, according to the definition, which states that the enthalpy change of formation is the enthalpy change when 1 mole of a substance is formed from its elements in their standard states under standard conditions. On the other hand, when constructing an energy cycle for a reaction using enthalpy change of combustion values, the arrows will always be pointing downwards according to the definition, which states that the enthalpy change of combustion is the enthalpy change when 1 mole of a substance undergoes complete combustion to form CO2 and H2O. Therefore, using method 2, this would translate to the enthalpy change of the reaction to equal the sum of the enthalpy change of formation of products minus the sum of the enthalpy change of formation of reactants when using enthalpy change of formation, while when using enthalpy change of combustion values, the enthalpy change of reaction would equal the sum of the enthalpy change of combustion of reactants minus the sum of the enthalpy change of combustion of the products. Thank you for watching. Please make sure to finish the assigned work and send it back to me as soon as possible. Thank you for watching.